Hello and welcome to today's class, which will cover sections 10.1 and 10.2, which deals with inflation. I'll go through, the usual routine. First, you should start on the Start Here page on Blackboard and check out the assignments, and because they do change from time to time. And you should read pages 302 to 312 in your text. That covers these two sections. You will be watching this instructor video. These lecture notes are critical to your success in the course, and if you really want to be highly successful, you need to work as many problems as you possibly can. So we're going to talk about inflation now and how it impacts the cost and the revenues and things like that, which we deal with. One of the most common, inflation refers to just simply the increase in cost over time to purchase goods and services. As an example of a service, if you bought an airline ticket then a year later you bought that same type of ticket, you're going to fly on the same type of aircraft, you're going to fly the same route, and it costs more. Well, that would be an example of inflation in the cost of that service, air travel. If prices go down, which they are with respect to air travel because of the pandemic, then that would be called deflation. And we're experiencing that, for example, with gas at the pump. It's actually less now than it was maybe 10, 12 years ago. So that's an example of deflation. We rarely get deflation, and it usually means something bad. In this case, it means a pandemic is causing a decrease in the amount of oil needed to make the gasoline. But inflation refers to the increase in cost of goods and services, and that is a very common thing, much more common than deflation. A common measure of inflation is called the Consumer Price Index. Actually, it's a measure of inflation or deflation. And the Consumer Price Index is a measurement kept by the federal government, the Bureau of Statistics, Economic Statistics, and they publish a new number every month, and so there's a yearly inflation rate and a monthly inflation rate. And the Consumer Price Index basically consists of a number of commonly used goods and services. As an example, food, energy, transportation, healthcare, and housing are all part of the Consumer Price Index. And what they look at is what does an American family usually buy, and then has that gone up in the last month if we take a weighted average of those things. And so equation 10.1 tells us that the dollars in period T1 equals the dollars in period T2. Now, this is where T2 is in the future from T1, times 1 plus the inflation from T1 to T2, from time 1 to time 2. I'm sorry, it's not times, it's divided by, there's a slash there, okay? It's divided by 1 plus the inflation. Now, this does not say the inflation rate. This is the entire amount of inflation from time 1 to time 2. And we're taking the dollars in period 2 and basically dividing by 1 plus the inflation rate between those periods gives us the dollars at time 1. So we can use this equation. For example, we could multiply through this equation through the thing we're dividing by 1 plus the inflation, if we multiply through the equation, we can put the dollars at time 2 in terms of the dollars at time 1. In this case, we're kind of deflating the dollars at time 2 because we're dividing by this. If we were to multiply through by 1 plus the inflation and get T2 in terms of T1, then we would be inflating from T1 to T2. The term constant value dollars refers to what the dollars are worth now, what they could buy now, as opposed to what it'll cost, say, in the future to do something like that. So equation 10.2 says constant value dollars equals future dollars divided by 1 plus the inflation rate. Little f is a term that's analogous to the I that we've been using for interest rate. It's analogous to that. It's a rate, and we divide the future dollars by 1 plus the inflation rate to the nth power. If there are n periods between the current time and the future time. Okay, so this is just kind of another statement of this, but it does it by period because f is a rate as opposed to a total amount of inflation. If we solve equation 10.2 for future dollars, we simply multiply through by 1 plus f to the n. We get future dollars equals the constant value dollars times 1 plus f to the nth power. So in this case, we're inflating the constant value dollars to get them out to the future. This works just like f given p and p given f, but now it's not the interest that's being that's causing the value to increase, it's the inflation rate. So I have a lot of experience with this in the aircraft industry, and in the design of an airplane, there may be a long period of time between the time when you're designing the airplane and you're doing production cost estimates and when the actual airplane is going to be produced, because with aircraft, especially advanced aircraft, if we want to call them that, there's usually, after the design phase, you build a prototype, you test the prototype, build several of them actually, so you build several airplanes, you test the prototype with test pilots, and they give you feedback, you redesign, and so on. So there could be, what I'm saying here is there could be as many as 10 or more years between the early designs and the final start of the production of the airplane as a unit. So during that period of time, inflation is occurring, and very often then what you estimated the production costs would be has to be inflated then up to get the true cost when the aircraft is actually going to go into production, maybe 10 or 12 years later. So this is what we did. We basically used this equation, 10.3, to inflate what it would cost now to build that airplane, which would be called constant value dollars, times 1 plus the inflation rate. Actually, we didn't just use, for example, the consumer price index for the inflation rate. We broke the airplane down into major subsystems, and each of those had a different inflation rate. And so we would apply that to the subsystems and then add it all up. But the bottom line is we were using this all the time because of the long time frame of our projects. I want to get into some definitions. So we call constant value dollars uninflated dollars. If we want to inflate them with the inflation rate F for n periods, then that gives us future dollars. And if you recall, the rate I that we've been using throughout the semester, we really didn't talk about inflation until this chapter. Actually, we're not going to talk about it again after this chapter, but we used the real rate or the inflation-free interest rate, I. So that I that we've been using theoretically is the inflation-free interest rate. Well, there's another rate that we call the adjusted rate, inflation-adjusted rate, which is I sub F. So the I sub F includes inflation. And this is also called the market rate. That's the most common term to use this. Inflation-adjusted rate, market rate is I sub F, okay? And that rate includes both the increase in price due to inflation plus the increase due to time and the interest rate, I. So we'll talk about that relationship here and some other equations, but the next chapter, the author actually defines the market rate, I sub F, equals to I, that's the real rate, real interest rate, plus F, the inflation rate, plus the product of those two, I times F. So equation 10.4 in section 10.2, which tells us how to adjust our calculations to account for inflation. If we have some future dollars, then we need to divide that by 1 plus F to the nth power. That takes out the inflation. So then I'll have constant value dollars here. And then I divide that by 1 plus I to the n, which takes out the time value of money. And so if we multiply these two quantities together, we get, this should be a capital F here. We get F times 1 plus I plus F plus IF. All I've done is multiply to the nth power. And so that is equation 10.4. And then, so by dividing by 1 plus F to the n, that adjusts for inflation. Then you're dividing by 1 plus I to the n, and that adjusts for the real interest rate. And we call the quantity that is I plus F plus IF, we call that the market rate. And if we take 1 plus I sub F, recall, is the inflation rate, the market rate. And that's equal to 1 plus I times 1 plus F, which is 1 plus I plus F plus IF. And if we subtract 1 from both sides, we get equation 6. That is, the market rate I sub F equals the interest rate, the real rate, plus the inflation rate, plus the product of the interest rate and the inflation rate. And then if we substitute equation 6 into equation 4 here, you can see that what we're going to get there, we get that P is equal to capital F times 1 plus I sub R to the n, divided by 1 plus I to the I sub F to the n, which is the same thing as F, P given F, I sub F, and n, okay? So that's equation 5. We kind of went backwards there, but I needed this equation to plug into this to get me to this. And then there's an example. If the real interest rate, I, is 6%, and the inflation rate, F, is 4%, then the market or inflation-adjusted rate, I sub F, is 6% plus 4% plus the product, which would give me, this is going to be 0.0024, which would give me 10.24%. So we're going to do an example of looking at what would happen to a lottery winner who has 3 options on collecting your money. That would be nice to be a lottery winner, I suppose. Although I don't think many of them have been more happy after they get it. Anyway, here's the situation. The lottery winner can take their winnings in one of 3 ways. And he says F is equal to, the inflation rate is 4% and the interest rate is 6%. So that's that will give us a market rate, which is the product of these 2 plus each one is going to be 10.24%. So you can either take, these are your options, 3 options. The red option is to take 100,000 right now. The blue option, number 2, is to take 8 payments of 15,000. That's each starting 1 year from now. Well, that's just an A series, right? Of $15,000 for 8 years. And then there's a third option. This is the green option, which is 45,000 now, 45,000 after 4 years, and another 45,000 after 8 years. So let's look at what is the present value of each of those using the market rate, which is 10.24%, which we found that on the previous page. Well, the present value of this one is just $100,000. Of course, we're going to forget about income taxes for now. The present value of Plan 2, which is an A series of 15,000, is 15,000 P given A. The market rate for 8 periods, that's $79,329. And the third option, 45,000 now, 45,000 4 years, and 45,000 in 8 years. If you plug in, and the 45,000 now is worth 45,000, that's why there's a 1 here. And then the 45,000 4 years from now, you have to multiply it on P given F, 10.24% for 4 years. And then the 8 years will be multiplied by P given F, 10.24% for 8 years. If you do that multiplication, you get $96,099. So the best option is to take your $100,000 now. Of course, that is before income taxes. So the outcome after income taxes might be a little bit different. And we'll learn a little bit about income taxes in Chapter 13. But for now, I want to just look at a couple of problems just to solidify this theory. The first problem, example problem that I'm going to talk about here is, in an inflationary period, the dollar-based currency, what is the difference between inflated dollars and then current dollars? Okay, there is inflated dollars and then current dollars. Remember, there is no difference. Inflated dollars are then current dollars. They're also called future dollars. I forgot to mention that in a lecture, that they are called then current dollars. Okay, so there's no difference. And then I go on to say, in industry, we refer to inflated dollars as future dollars, or future dollars as then current dollars. Part B. What is the difference between then current dollars, future dollars, and constant value dollars? Well, remember, that was one of our equations, to convert from future dollars to constant value dollars and vice versa. Those were equations 2 and 3 in Chapter 10. So the difference between then current future dollars and constant value dollars is that then current dollars include inflation and constant value dollars do not. This is expressed by equations 10.2 and 10.3. Constant value dollars equals future dollars divided by 1 plus the inflation rate to the nth power. Dividing by 1 plus the inflation rate to the nth power removes inflation. Okay. Future dollars equal constant value dollars times 1 plus the inflation rate to the nth power, multiplying by 1 plus the inflation rate to the nth power adds inflation. So that's how we do it. Notice that this is exactly the same as interest rates and future worth and present worth. Only when we were doing that, we used the rate I, the interest rate. Now we're using the rate F, the inflation rate. Okay, this will be the last part of today's lesson. This is example 2. According to the data of the National Association of Colleges and Employers, engineering graduates' average starting salary of $61,872 were among the highest of all majors of the class of 2011. What will be the average starting salary amount in 2019 if salaries increase at the rate of 2% per year? So let's look at that part. Using equation 10.3 and F equals 2%, we get F, the future value in 2019, equals P, which is really constant value dollars, 2011, times 1 plus the inflation rate to the nth power. And of course, that inflation rate is 2%. So F 2019 is equal to 61,872. That's essentially constant value dollars or present dollars. 1.02 to the 8th power gives us 72,493. Part B, what if the inflation rate is twice the inflation? What if the rate of increase of salaries is twice the inflation rate of 3.5%? So 2 times 3.5% is 7%. So it's asking you, what will the future average starting salary be if they went up by 7% per year? So the future value in 2019 is the constant value P in 2011 times 1 plus F to the 8th power again, but now the F is 7%. So when we multiply 61,872 times 1.07 to the 8th power, we get 106,308. So that concludes today's lesson on sections 10.1 and 10.2. Thank you.